want to begin to get into some of the ideas of the quantum world. So moving into the second unit of Physics 305, the two main topics I want to look at here are the ultraviolet catastrophe. To understand that better, we want to look at the idea of blackbody radiation, and then also the photoelectric effect as the first evidence of Planck's constant and the quantization of energy. So something that may look familiar from chemistry classes is Maxwell's distribution, which gives us information about the velocity of atoms versus how many atoms are at that particular velocity. So when atoms are moving more slowly on the whole, we know we're at a lower temperature. So this is going with the idea that temperature and the speed of atoms are somewhat proportional. So at a temperature of 1000 Kelvin, what we find is that the speed of the atoms is much faster. And the velocity distribution also tends to be a bit wider. So with this higher temperature comes faster moving particles, and we know that that's more or less, these are more or less equated with each other. Same thing with slower or with a lower temperature, we have particles that are moving slower, and the peak is a bit more concentrated as well. There's a smaller distribution of particular energies. All right, this is going to lead into, I guess, a more appropriate way of thinking about these in terms of quantum mechanics, which is the Blackbody radiation curve. It's a very similar type of idea. And the general principle of blackbody radiation is this statement up here that all heated bodies emit electromagnetic radiation of different wavelengths. Now, remember, electromagnetic radiation is not radiation like nuclear radiation. Rather, it's just light. We're used to a narrow spectrum of visible light running from the blues and violets up to longer wavelengths and reds. And any material that is heated up to a certain temperature will eventually glow in certain colors that we can see. So here I'm showing an example of a little filament that is being heated, and we can see it glowing sort of an orange yellowish color. Here is a bolt that has been heated quite a bit, and it's more in the red color. And here is an example of a furnace which is heated to very large temperatures, and it's glowing sort of a red yellow. Now, a perfect example of an object as well are stars at certain temperatures, and we get certain colors at those particular temperatures as well. So one of these FETs does a nice job here of showing some different changes. So to get a sense of our landscape here, we have a temperature controller, and we get a sense of the wavelength. Here it's measured in micrometers. And there's this band here of visible light. So this is the range that we can see light. So for a temperature around 4800 degrees Kelvin, most of the intense peaks are in the visible. If we go to the temperature of the sun, if we let this little gauge go up towards the temperature of the sun, we can see that all of these highest peaks are visible light. Certainly there's energy that's being emitted in the infrared, and then also the ultraviolet. You know, the ultraviolet is, of course, the ones that are a little bit more dangerous for us. But this is no coincidence that visible light to us is where this peak radiation is. It's simply a matter of that's how life evolved. We evolved to see this peak radiation because that's most of what there is. Therefore, organisms would find it beneficial if we could develop a sensory system that could, quote-unquote, see colors where we have most of the colors. It'd be interesting to note that if there were a planet out there with a star with a temperature that was maybe around, let's say, 3,700 degrees. So if we want to try to zoom in on this, we'll raise the peak. So we might find on that planet that organisms are adapted to see in a range instead of from here to here, which you're only sort of catching this tail end. Maybe they would adapt to see in this range instead, where they would see from 500 nanometers up to about 1500 nanometers. That'll be very interesting to note if we start discovering life on other planets. And then as the temperature lowers further and further to, let's say, that of an oven, it looks like the peak just completely drops off the planet. And that's just because we need to zoom in on this a little bit more. There we go. If we zoom in on it far enough and then zoom out on this scale, we can see that this peak is much more in the microwave range. So it's not very visible. It's not visible at all for us, but it still emits energy in the form of radiation. And as you note, as the temperature is going up, the peak is growing quite substantially. It's by a factor of temperature to the fourth power. So that the peak grows, but we also see that the peak is shifting over towards the left. So we have the peak is present here, nowhere close to the visible light spectrum. But then as we back this out and raise the temperature, we see that this peak is beginning to shift further and further towards the left. I think I went the wrong direction. Yeah, there we go. There's our peak. So this peak was shifting further to the left. So the ultraviolet catastrophe. So this curve was experimentally studied and understood. Well, it wasn't understood. It was experimentally studied. So experiments showed this peak here. However, theoretical predictions suggested this peak, which we call the ultraviolet catastrophe, which says that mathematically it's expected that this radiation intensity should just keep blowing up toward infinity. So classical mechanics has been working great to describe the total energy of a finite number of particles, but it's been working terribly for describing an infinite number of available vibrating modes. And the picture on the right is just an alternate view of intensity versus frequency rather than versus wavelength. So to understand this ultraviolet catastrophe better, we need to get a sense of how they were trying to describe the way that blackbody radiation worked. And essentially the idea is that you allow energy into a blackbody. And usually this was just some kind of material hollowed out that you could let energy into, and you could seal up and let the energy bounce around. So as it's bouncing around, whenever this energy, this light, hits a wall, some of that energy is absorbed into the wall. It causes the atoms of the wall to vibrate and possibly to release energy at a different wavelength. So as with the strings of a guitar, for instance, you could pluck the string at some particular frequency, and what happens is that not only is that fundamental frequency selected, but we get some other frequencies. What I'm going to do here is drop this back so that we just have the first frequency. So an example of the fundamental harmonic of a vibrating string. But by putting an amount of energy in that can cause this vibration, that vibration can also stimulate the next vibration up. So we would get the second harmonic as well. So this one could also be caused to vibrate. So essentially you could take this first vibration and turn it into a second vibration. This is what theory suggested would be possible. So the second vibration could then promote the third, which could promote the fourth. So you could have an infinite number of vibrations. You just put in a fundamental vibration, which could trigger each additional vibration after that. So a picture that I like from a text I've used in the past is this piano with an unlimited number of keys extending to the ultrasonic region, all the way out to infinite frequencies. So the equipartition law would require all the energy supplied by a musician to one of the low frequency keys to travel all the way into the ultrasonic region and out of the audible range. So if we strike the lowest key, what that theorem would predict is that that could trigger the next key to go, which could trigger the next key, which could just keep triggering up to infinite energy. Except that that's turned out to not be the case. Instead, there needs to be some kind of other resolution. Now, I've used this diagram in the past to help try to understand this situation, but I think there's a better way to look at it, which I'll get to in the coming slides. So Maxwell Planck went into his physics cave for about 6 years to work on this. And the mathematical expression that he came up with was this idea that an energy has to be equal to some new constant with a value of 6.626 10 to the minus 34th joules times seconds, multiplied by the frequency of the radiation, could be considered the energy of quantum radiation. So if we started at ground state, if we absorb a certain amount of energy, we can go to a first state, absorb another of the same amount of energy, we can go to the second state. And we'll see that this picture looks very similar to our understanding of atomic orbitals at this point. But this is a very new picture back then, and it had some interesting consequences if you said that energy could only be released in particular packets of this size, h times frequency. So I want to use an example of bouncing light balls. So we're going to say that this outer circle is our black body, and we're going to set 8 red photons loose inside of this. So we're going to say each red photon has a frequency of 2. And we're not going to worry about units here. We'll say they have a frequency of 2, and we'll let h equal 2. So that we can do a simple calculation that the total energy of all of these is, there's 8, and the energy of each one is h2 and frequency 2. So it gives us a total energy of 32. Now, by conservation of energy, we know that anything resulting from this cannot have an energy that is larger than 32. Now, I'm going to pause this video here and finish it in the next one, since I've basically run out of my 15 minutes.